And let me share my screen. Can everybody see my screen?
Yeah.
Yes.
Good. Right. Put my volume up. Good. Okay, so we'll make a start. So hopefully most of you have had feedback on the test, and hopefully we've had our one-to-one session so that you've had a chance to reflect on the first test. So the first test is only worth 30%, and it's really just there to give you some idea about how you're getting on. But there's still 70% of the marks to be gained. You only have to pass the very final overall module, so it doesn't matter if you go down below 50 in any element of the assessment. All that matters is whether you get 50% or not. So the second test is worth 30%, and it's going to be on the week beginning the end of the week, Friday of the 29th of April, and then the coursework is the week after that, and then we've moved it to the Monday. So it's week 15, and then if you go after that to the Monday, then you'll have the weekend to actually complete the coursework. Does anybody have any questions on that schedule? Good. Okay, so we've got 3 main units to cover. So this week we'll do future cryptography. So that's covering zero knowledge proofs and homomorphic encryption, and give you an idea about where cryptography is going. And then we'll have 2 presentations on host-based security, and especially how we link a host into a domain. So how does a host become part of an Active Directory domain? How do we make sure that we can actually link a host into domain and apply trust into that? Okay, and then the last test will cover the units that weren't covered in the first test. So I think that goes from digital certificates, tunneling, blockchain, future cryptography. So I'll give you a study guide like the last time. So if you remember, that was the study guide, and it gave you a kind of heads up on the type of questions that we were going to ask. And I'll prepare a little video for you to give you a heads up. And then I'll add some sample test papers and some sample exam questions. And if you've got some time before the Easter break, then maybe ask then. But obviously the Easter break is probably when you'll be doing most of your studying and doing the coursework. Anybody any questions on that? No? Good. I just want to check. The last time I had a problem with my headset. Could just somebody say hello?
Yeah, we're here.
Hello.
Okay.
Hello.
Good.
Hello.
Good. Okay. That's excellent. And everybody can hear me. Yeah. Yeah.
Yes.
Yeah. Good. If anybody have any questions, please don't worry about interrupting me in anything that I say. So I know it's difficult on a web session to engage sometimes when there's a lead on. Okay, so this week we did blockchain, and the lecture should be there as was presented, and also the PDF. There should be the code, and the lecture should also be on the GitHub there too. So there's probably no need for me to go over the lecture unless somebody really wants that to happen. Does anybody want to go over the lecture again, or have you watched it, or maybe you're just having a rest after the first test? But the practical side is important, and we're using Geth to be able to set up our own Ethereum blockchain. So we've implemented it this year in Linux. So in in that we go through the main steps about creating. So within a blockchain with cryptocurrency, we can't actually create any more cryptocurrency once we've created our Genesis block. So you'll find in the lab we create 3 accounts with private keys and with IDs, and they are given some cryptocurrency. From that, we then create our Genesis block. So this is our JSON file for creating our Genesis block. The level of difficulty for the miners is set quite low because we're running in a virtual environment and you don't have a lot of memory on your computer, on your VMs, and also we're running the blockchain and the miners on the same VM. So that level would be much higher, and we generally ramp up the difficulty as we go along. With Ethereum, we pay the miners in gas for the work that they actually do, so we define things like gas limits. So this is us creating the blockchain here with to create our Genesis record with the 3 accounts that we've created. That creates a public key and a private key pair using elliptic curve methods. We keep our private key secret, and the public key is used to sign transactions onto the blockchain. So did I say that right? The private key is used to sign things onto the blockchain, and the public key is used to verify the signer. It works magically in that when we sign, it automatically links the private ID with the public key, so we don't have to present a digital certificate to prove our public key. The signature that's applied using the R and the S value automatically verifies that we are the signer. If I have that public address, then I have signed it with this private key, and that's really the magic of a blockchain, and that we don't have that whole PKI infrastructure. Okay, so if you go ahead and we run our Geth, which creates our blockchain and maintains it, and then we go ahead and perform some transactions, such as transferring some cryptocurrency from this account into this account. We get a transaction value, and this is a signature here with the R and the S value. That actually defines that this is a trusted transaction that was signed by this entity here, and we automatically know that is trusted because of the way the elliptic curve actually works. After that, we'll see that nothing happens until we start the miners, and once we start the miners, we'll see then that they go ahead and mine, and we can see the blocks being created. After that, we've got a simple contract, smart contract that we create in Solidity, and then we can go to this website here, and it creates the code. This is the binary code here. This is almost like the machine code that's created that runs off the blockchain, and all the other stuff is really setting up our contract and making sure that it has the right account for running the code. So that's what the code looks like. We create a JavaScript file, and then we apply the smart contract. This is the binary code in here to actually do that. Okay, so we load that up onto our blockchain, and then we can actually do some testing. We can look at the smart contract as it runs off the blockchain, look at various things, and then actually run it if we need to off the blockchain. Remember, you've got to have gas in your account on Ethereum, because nothing will run, and the smart contract won't be mined until the miners get paid. So we've got a little bit of math here, a little sort of math function that you should be able to get working. And then obviously in a real development environment, you wouldn't be putting your code into the web page. You would be running a compiler to create your smart contracts. So in the last part of the lab, we install the Solidity compiler, and then we can compile our Solidity code into binary format. We can see that produces the binary code that we saw before when we used the web page, and we can also use an ABI option, which gives us the wrapper code that we see that we applied into the JavaScript code. Okay, and all the commands I've outlined there. Has anyone had a chance to look at this one? I've also got a Windows, the Windows version. I don't know if anyone who's running a Windows Ethereum blockchain, it's all typically Linux now. Did anybody have a go at this lab yet?
I tried a little bit of this lab, and I got to the point where I created my Napier, and I tried to read my Napier, and I don't have access to it because
Yeah.
once I do sudo, I don't have access to it anymore.
So if you do your change mod of 777,
I
then
tried that, and
sudo, if you do sudo change mod 777, it should be okay.
yeah, it refused to do that as well.
Yeah, so just let me jump on to my VM. Let me get logged in. Okay, so here's my Napier. And so I've just let me see. There we are. And find my Napier folder. So I've changed it. If you do a sudo, then it creates it as a root, but you don't necessarily have to create it with sudo earlier on. But if you do, then you should be able to do a sudo. I'll change mod to 700, and that's what you should see. So you can see that my Napier, when you create it, you'll get this, and then when you try to go into my Napier, you'll not be allowed. So if you do a change mod or 777, my Napier.
What might, sorry, Bill.
Yeah,
what might be easier is if you did a own
yeah,
and changed it from
change the
root
owner.
to Napier.
Yeah,
Then you
yeah,
might find that easier.
yeah. That's probably an easier way. This is just a kind of quick fix way. But yeah, if you change the owner to Napier, then that would take back the rights from there. But
Thank you.
yeah, once you're in, then you should see a key store folder, and that's your keys in there. So I've got 4 keys. I think when I created from Geth and the other 3, I created from the command line, but they should look 5. See 03. Where are we? 003 03 2 0 T 1 3 2 2 4. have a look in the, that's what your keys look like. So there's a salt value, yeah, your private key is in there, and then your public key. It's obviously protected with a password. It's quite simple, but any time that you need to get access, you need to put that password in. So that's the reason for the EAS in there. Obviously, we're using an elliptic curve public key for a key pair, but we protect this with EAS encryption. We use a key derivation function such as bcrypt or pbkdfs2 to be able to generate the key from the password. So if you think about it, I put in QWERTY1, it generates say a 256-bit EAS key. That EAS key opens up my private key on the system. Okay, and if you go into the Geth folder, I've got rights there. This is what your blockchain actually looks like. So there's the chain data. Looks a bit boring, but that's the blockchain there. And so what we do is we create blocks as we go along, and each of the blocks are hashed, and then there's a link back to the hash of the previous block, and our block links to the next block. So once you've created your Genesis record, then that's it. There's a mutable recording of all the transactions that have run on the blockchain. Does anybody have any questions about that? So we've used Ethereum because it's a good example of a second generation blockchain that integrates the concept of it's improved proof of work, where we have miners doing work for us, and it also integrates smart contracts into our blockchain.
I have a question. So I have seen the lecture but haven't done the lab yet, so maybe that's a problem. But from the lecture, it wasn't very clear to me how the actual coins get generated.
Yeah, well, they're created initially from the Genesis block. The lab should show Genesis block being Genesis block being created. So just let me find my lab again. Sorry. Okay, so in this case, we create 3 new accounts that have public keys and private keys. Then we create the definition of the Genesis block. So this means that this account has this much gas, this account has this much, and then that account has that much. So that's all our cryptocurrency that we've created. So we can now go ahead and transfer that money, create new accounts, and also to pay the miners. So once we've created the Genesis block, then that's all of the cryptocurrency created, and really all that happens is that Bob pays Alice, Bob goes down 1 gas, and Alice goes up by 1 gas. We can't create any more cryptocurrency.
Thank you.
Okay, anyone else with any questions? If you want, I could quickly go over the lecture again. Maybe I can highlight some of the key points from there. Just let me try and find where it is. So the key concept is that it's a peer-to-peer transfer, and there's no intermediate banks involved in the transfer, and each transaction is signed. So Bob finds out Alice's public ID, then creates a transaction to transfer a set number of bitcoins. He will then sign it with his private key, and then that transaction goes onto the blockchain if the miners agree. So that miners create a consensus as to whether Bob has enough currency in his account. So they look back over all the transactions and divvy up how many bitcoins he has, and do a quick check to see if he hasn't sort of double spent in the current block. And then if he has enough money, bitcoins, then the transaction can go ahead and is added to the blockchain. With Bitcoin, it's about every 10 minutes a new block is created and a new hash is applied onto the blockchain. But it was Satoshi Nakamoto who created the original Genesis record all those years ago. In 2009, he created this. So this is the original Genesis record, and what we see is the hash that the miners had to produce had a certain number of zeros at the start. That has become more and more difficult. So they race to find a nonce, and whoever finds the nonce when taking all the transactions, and it ends up with a hash that has got so many zeros at the start, they win and they get the reward. Unbelievably, the first reward was 50 bitcoins, which is a lot of money now in fiat currency. No one has claimed that. So Satoshi Nakamoto hasn't claimed for all of the money that he made or he or she made at the very start of this. Okay, so the typical block now is 1 megabyte, and it gets full virtually every 10 minutes. So sometimes you've got to wait 20 or 30 minutes because the blocks are too full, and that's a worry from there. There's a Merkle root, so we can actually define the root of the Merkle tree to make sure that all the hashes are correct and that it can be verified. And there's obviously a time that we have in there. We link to the previous block hash and the future block hash, so it locks it all in. Okay, so that's what we see when we look at someone's account. So we see the address. That address is generated from the private key to produce a public ID, and we'll see the number of transactions and so on. So nothing is really anonymous in Bitcoin. It's pseudonymous. If I know your Bitcoin address, I can see all your transactions and who you're paying and so on. Sometimes you'll get one sender will send to multiple recipients, or many recipients will send to many and many senders will send to many recipients. So it doesn't have to just be a one-to-one transaction. Okay, so that's what the transaction looks like from there. And this was a massive one here. So I think that's $12 million there in a transfer. So there are some large values going on. So the transactions kind of went up to a peak before it kind of crashed. People were just using it to make money, and it had to stop sometime, so it kind of crashed, but it's picked back up again, and it's kind of equivalent to where it was in about a year ago. But obviously, Bitcoin is a very poor cryptocurrency and can only be seen as version 1. Oops. Let me try and find where we are.
Can I ask a question?
Yep.
So, in order to work out how much coins somebody has in their wallet, does this mean that the workers have to start from the very root of the tree and then calculate all transactions that ever happened?
That's right. So
So
they will
with
look.
time, the blockchain becomes slower and slower the more transactions there are.
Yeah, that's right. But they've it's generally scaled up pretty well. So you can create your own nodes, and obviously there are many miners around. I mean, the worry, as I'll come on to, is that we someone can hack the system if they take over at least half of the mining process, and they can actually define the transactions that are valid, and they might roll back a transaction or not accept it or add their own transactions in there. So there is a scale that you get to that this has to be completely distributed and no one takes over control. The GitHub is controlled by people who hopefully are trustworthy, and we wouldn't put backdoors into the software and so on. So no government controls this infrastructure, and it's run for the last 9 years or so. So there's obviously that risk, and it happened with Ethereum that there was a hack, and they had to decide whether to create a hard fork, whether to stop the blockchain as it was running and to create a new one, or to roll back. So nobody has ever really rolled back a blockchain to say that all these transactions weren't valid, but that could happen. Uh, and also there's been general consensus about changing the parameters of the blockchain and for it to be updated whenever there's been bottlenecks. Does that answer your question?
Yes.
Okay, thanks. Oops. Just let me go back to my presentation. And again, I mean, we saw high transaction values happening last year or so, and then it's kind of crashed a bit, but it's back up again, and it's fairly stable. The value peaked up at 20k unbelievably, and it settled about 4k, and it's not really moving much. So it could have found its optimal point, but it's all to do with supply and demand. The more supply there is of bitcoins, of people selling, and if there isn't a big demand, then price will drop. If there is a demand for them, the supply is less, then obviously the price goes up. So it's not quite as stable as fiat currency markets. Just a minute, get me that. And there's thousands of cryptocurrencies. Obviously, Bitcoin, Ethereum, Ripple, XRP, and so on. They're the top ones. Monero is an interesting one. IOTA is third generation blockchain, instant consensus. You can see the valuations aren't that great when you think of fiat currency valuations, but 71 billion for Bitcoin is not too bad. But obviously, if you go down to number 1,000, anybody can create their own cryptocurrency, and obviously we can build up our own ecosystem with our own tokens that could be converted back into fiat currency. Some of them are tethered, so this one here is tethered to a dollar value. When Facebook release their cryptocurrency, they're going to link it to fiat currency. So Facebook will put a certain amount of money away in reserve so that if everybody tried to cash in their Facebook cryptocurrency tokens, then they will be able to get their money back. That's a kind of scary thought, that they would become the largest central bank in the world. They would also be able to link your purchases to your adverts and so on. But they reckon that Facebook are looking at this as a business model, not to make money on the cryptocurrency, but for Facebook coins to become a kind of legal tender in terms of purchasing things online. And from a user point of view, it doesn't expose your Visa card or your bank account. you only have a certain amount of Facebook coins, say, in your account, and you would just top that up, or you could transfer uh, Facebook coins to other people and barter and so on. And then only when you need to convert them back into fiat currency would you have to convert them into something. Any questions? So this is how it works. This is the magic of it. We create our 256-bit private key. It's a random value. Don't let anybody create that for you because they might, or don't let anybody untrusted create that for you. There was a hack recently where an online company created a GitHub. They paid for Google adverts, so they appeared as a top search. And so when you went to generate the seed required for the cryptocurrency, this company kept a copy of your private key, and then they went and hacked a whole lot of accounts. Everything looked credible, but it was actually a big scam. So this is the value that's stored in your wallet, and this is your private key here. It's converted into base 58 because we get rid of the difficult characters such as 0, and we end up with 58 characters here, so it's fairly easy to print them. They typically start with 5 or a 3, a 1. That's how you identify them, and there are a certain length which relates to the length of the private key. So then we take our elliptic curve, and as you remember, we multiply our G value, which is well known to everybody, and we know the prime number, and then we multiply that point by this number of times, and we get this point on the elliptic curve. We then take that point and we stick it through a few hashes here, and then we convert it into base 58, and then magically we get your ID here. That's got a 1 at the start, and you'll see that as your Bitcoin address. So my mobile phone, when I want to send you some cryptocurrency, you send me this ID, and then I make a transaction, and that transaction goes on to the blockchain, and you should receive your cryptocurrency. I don't have to transfer anything to you, but I sign it with my private key, and it's verified. Does anybody have any questions on this? Good. If somebody gets your private key, then there's a very good chance you'll lose your bitcoins because they can sign on your behalf. Okay, so that's what it looks like. There's your address. It starts with a 1 at the start, and there's also a hash in there. If you want to send someone, to make it easy, you'll take your phone and you'll do a QR code scan, and that will generate their address for you, and then you can go ahead and transfer it. So obviously once you've done it once, then it's easy to map that again so you can have other transactions. Okay, so there's the basic process of creating this private key. Then to the actual address, that's the procedure that it goes through. So this is a real address here. You can go into a security site and have a look at this, but there's the private key, 256 bits. There's the public key. Remember, it's a point, so it looks like 512 bits or so. You have your private key address that is stored in your wallet, and then your public address, which is this here. The signature looks like this, a whole lot of hex digits, but this integrates your private key and makes it provable that you signed that. Okay, so that's the transaction there. We have a signature, and it integrates the public key of Alice into it, so we can almost instantly check that that is a valid transaction. All we need to do is to get Bob's public address, and then we add that onto the transaction, and that's it. So with our miners, the miners go ahead and look at all the transactions that are happening within a certain time window. They create a consensus, they compete against each other in Bitcoin, and then the first one to produce the hash is the one that wins and gets the reward, and then we have a new block mined. So the miners are obviously in big pools, and there are large arrays of GPUs that these companies have, and they're consuming the electrical power of a small country like Ireland just to be able to create these blocks. So it's a very inefficient method of mining. So you can see here it's generally a good part of the mining is controlled by some of these really big companies. Those companies are based in places where they have cheap electricity, such as China or perhaps Iceland, where there's a ready supply of cheap energy. The hash rate itself gets more difficult as we go on, because we want to make it less attractive for the miners, because we have less coins around and we don't need the miners as much as we go through. So eventually we'll run out of cryptocurrency and there'll be no more cryptocurrency left, and then there'll be no need for the miners to create it. So the hash process where we are just now is that the miners will race to find the nonce value with all the transactions that will create this hash value with a certain number of zeros. We use SHA-3 as our standard method of creating this hash. Did someone have a question?
Yes, Bill, sorry. So I guess this is what's confusing me. So you said that the number of coins are initially defined when the cryptocurrency is created, but then you're saying that we need miners, which
The miners do the transactions, yeah.
okay, do the transaction.
Yeah.
Right. So if you want to, and then you're saying that we don't need. You said we wouldn't have the need of miners at some point, but why is that?
We will need miners, but the miners there will have to be a reward there within the Bitcoin. Ethereum is better because Ethereum pays the miners for the actual work that they have done, and not make it a competition as we do in Bitcoin. So Bitcoin is a big competition, and whoever wins that block will get 12.5 Bitcoins as a reward, and that will obviously be released, but eventually we'll run out of cryptocurrency, and we'll have to find other ways of, well, we have the amount of coins in the whole infrastructure will then be static.
Okay, so there is something like a reserve of bitcoins that nobody owns.
Yeah.
They go to the miners as a reward for their work. Is that right?
Yeah, that's right. Yeah. So Satoshi defined this as to release the currency onto the market at a rate that the market would adopt, and he got it pretty right. He or she got it pretty right, and that, I mean, there was a big peak, but it has generally settled down. If you release the coins too quickly, then it will lose its value. If you do it too slowly, then the coins go up too much in price, and it could crash. So it's pretty much there. I mean, I think the very simple math that was applied has kind of worked, but we will run out of cryptocurrency. The worry is that we'll lose it. People lose their private key. Once you've lost your private key, the cryptocurrency can't be spent anyway. And it happened when someone died in Canada. They were sitting on all this cryptocurrency, and they can't find the password to be able to open up the wallet, so that cryptocurrency can't be spent. The same happens for the first 7 blocks or so. Nobody has came forward with the key for that, so that's unspent money. It's billions of dollars sitting there, and nobody's spent that money.
Wasn't there a case where somebody in Yorkshire threw away a hard drive that had got cryptocurrency in, and they went sifting through the landfill for it?
Yeah, it's quite shocking. There was a case where some criminals tied somebody up in a house. I think it might have been in Yorkshire too, and they forced the person to give away their password on their wallet, and it's almost impossible for the police to be able to trace those transactions. So it's almost like a perfect crime. So it's almost impossible to find out who actually uh, uh, did stole the cryptocurrency, because it's not like a coin that you go into a computer and steal it. All you have to steal is the private key, and then make transactions, and then move the money quickly, possibly into another cryptocurrency method, move it around, and then leave through an exchange.
I think there was an update on the Canadian case.
Uh-huh.
They managed to find the private key on the laptop, I guess through forensics. And
Hashcat. Yeah.
yeah, they opened the account and it was empty.
Yeah. There was is rumors about that person and some of the business that he did, and so on. So I don't think the full case has been seen yet, but it's quite worrying that people trust people to hold their cryptocurrency for them. But just watch your private key. My advice is not to put your private key online, not to have your wallet online in any way, but to have a paper copy of your key with the 12 or 13 phrases that would recover the key. So if you were in an accident or so, then somebody could go to a safe and open it up and recover your key without actually doing it through a password. Because Hashcat can easily, if you put QWERTY123 on your private key on your mobile phone, then you're just asking for trouble. Okay. Good. So that's what a block looks like. There's the rewards. There's the nonce value that the miner has found to produce the hash value, which is all these zeros. The more zeros, the more difficult it is. So that's the way that they keep increasing the challenge. And there's the previous block and the next block. And a little bit of transaction fees in there for that. But you can see the size is about 1 meg. That's where we are. And there's some people debating about whether we should have a bigger block size, because 10 minutes is quite a long time. If you buy some coffee in Starbucks and pay with a Bitcoin, it's going to take you 10 minutes for it to really clear onto the Bitcoin, so that Starbucks knows that the money has been cleared. Okay, so Ethereum, the first big application of smart contracts and creating an e-commerce infrastructure with tokens was CryptoKitties, and that was successful because you could actually buy a digital artifact almost for the first time, and it was yours, and it would morph and change and so on, and you could sell the kitty on for a certain amount, and it was so popular that they thought that Ethereum had reached the limit around here, and that we couldn't go any faster. But luckily, since then, the rate of transactions has kept increasing, and we're looking at new methods of increasing the throughput of the transactions of Ethereum. It's nowhere near the rates of Visa or PayPal, but it's certainly keeping increasing, and it could be a contender in the future. But less focused methods such as Ripple are looking at instant consensus, but they're not actually a blockchain type method. Okay, so the Ethereum was created only in 2015. It's been a great success, but it was hacked in 2016. Then they created it split into two, Ethereum Classic and Ethereum, and they both exist. and it just shows you how a hard fork can exist. You fork it off on the GitHub, and you create a fork on the blockchain, and then you have your whole new block, which is created for you. So the transactions come in, the miners go ahead and process and find the block. They are then paid through the amount of work that they do to create the hash, and also for the amount of bits in the data. So the more bits that you create in your smart contract and within the data, the more expensive it becomes. So it forces developers to be very, very efficient in their coding. If they create too big space on the blockchain, it will become expensive in gas and it'll cost them more. So we just want to be able to get the sweet spot, to have enough code and for it to be efficient, so that it doesn't cost us too much in terms of gas values. Okay, so that's the gas that gets paid, and we can define that in our original Genesis block. The miners, you advertise a gas value for the contract, but the miners only, and it becomes more attractive for the miners if you advertise a high value of this contract, but the miners will pay you back for the amount of work that they've done. So you might advertise a contract as having a high amount of gas, and miners will be attracted to it to perform the work for you. But then if it's only a little bit of work, then they don't charge you for what you've advertised from them. Miners might not even, if you advertise it too low, the miners just might ignore you because they're too busy servicing other contracts which are worth more for them. Okay, so we can take it down into small amounts. We have ether or a gas. The gas is 1 unit in Ethereum, or we can define it as a ether cryptocurrency. Okay, so we can create a smart contract on the blockchain between Bob and Alice, and then the code will now be defined exactly for that contract. So it might be a marriage contract that they provide their identity into the smart contract, and the smart contract will define that they are now married. This is what our Solidity contract looks like when we saw it before. It's a kind of JavaScript type format that we use. We can compile it with Solidity. We define the compiler that we're using. So we need to know the compiler because it will update as time goes on. So we define our compiler version, and it'll compile into our binary code, our bytecode. We have a gas value for it. It needs to be enough to interest the miners, and we define an account which is going to run the smart contract. That's usually a trusted account that has enough gas in the account to be able to pay for the contract to run. This is what we could look like in the future. We get attestations for things that are signed, and I know that those attestations could run automatically against smart contracts. So in this case, we have an NHS contract that if someone has diabetes, then they'll get a discount from Boots. So they go along to Boots, it knows their identity and the attestation that they have type 2 diabetes, and they might get a discount from Boots. So in that way, we can actually run things ubiquitously without filling in forms and so on. So in terms of what this looks like, then like future system, if we looked at a 7-layer model, might look like this. Just like in the 7-layer OSI model, we have the Ethernet and physical data link at the bottom layers, and then IP, TCP, session, and so on. Our future systems could be built with a foundation of cryptography. Then we use strong software engineering methods to link into that cryptography, and then from that we build rights, accounting, governance, value, and then finance at the top. But each of these layers interconnect and link together and make sure that we have a solid foundation which is trustworthy. So the core of this is the Merkle tree, as I showed before, and what we do is we take our transactions and we hash them, and we take two together and hash them, and we take these two results and we hash that, and then we hash at the top. So it's a very efficient way of knowing that we have certain transactions there, because we just have to prove a certain part of the tree to know that a transaction actually exists. So it's impossible for us to insert anything or change anything or pretend for things to have happened. The Merkle tree supports that. So we add that hash onto the block, we link back to the previous hash, and then we take the hash of the next block, and that becomes part of this block. In this way, we make sure that it all links together. So the future might be towards an anonymized blockchain, because once you've put something on a blockchain, you can't get rid of it. So we have permissionless blockchains, such as Ethereum, and with that, they are public. So if you put your date of birth on there, your date of birth is going to be on there forever, and it can't be taken off. Along with that, when the elliptic curve gets cracked, then somebody could crack the signing process and release data and so on. So we can go for a permissioned blockchain such as Corda or Hyperledger Fabric, where a number of organizations share information, but it's not public. It's, say, within a bank, we could run a Hyperledger infrastructure. Often what we do is we put public keys onto there to prove identities, and then we would anonymize. So Zcash and Monero anonymize the transactions. Bitcoin doesn't do that. There are a new method called Mimblewimble that might look to anonymize Bitcoin. So you wouldn't be able to tell who the sender and the receiver was and what the transaction value, but it's not quite there yet. Then at the upper layers, we can do things like anti-money laundering, regulation, or healthcare, and where we would reveal that it was Bob that was that entry on the blockchain. Okay, so that's our transaction. We sign with a private key. We add the public key onto the signature, and that will prove that it was Bob that signed that. Okay, we use standard elliptic curve. The first method was elliptic curve DSA that was used to sign. And that's what it looks like. There is an R and an S value, and it's these R and S values which are used to sign and that prove the private key. And then we verify that with a bit of math that will prove that the person with that private key and public ID was the one that signed that transaction. Unfortunately, what was happening is that there was transactions like this, and with this, everyone has to put their public key, and all the public keys have to be checked. So it was slowing down Bitcoin greatly. And we see here all these public keys had to be checked and so on. So we came up with a SNOR, or native multisig, which allowed multiple signers to merge their signature together into a single signing entity. That was good because we could actually hide the identities of the signers, and we create a single signing, and it only takes a little bit of computation to check that. This is what happens. We take all the public keys of those involved in the transaction, we merge them together, and we create a single public key for that transaction, which is really all the public keys of the entities involved in the transaction as a single key, and we can easily check that that's a trustworthy way of doing it. And it happened in this block here, 47712, that they implemented the SNOR, or native multisig, and the companies got together doing the mining process, and they agreed that this would go ahead and we'd implement that, and this was the first one here that actually got that set up. So there are times on the blockchain when everybody's got to upgrade and move on, and then there can be some legacy code that people are still using an old version that really is insecure. Luckily, that really hasn't happened that much at scale, but we could have systems that we didn't quite agree the way forward, and we might have a hard fork, and Bitcoin might go off in two directions, and that can cause lots of problems. That bit here actually just shows the difference in the signature. Again, it's an R and an S value that you look for creating that signature. So some cryptocurrencies are looking at hiding the information. So one way that Monero is doing it is with what's called a ring signature. So a ring signature means that I can get together a whole lot of people with the public keys, and I can sign it as Bob, but I can make sure that I can prove that it was someone in this ring who signed it, but in this case Donald can't tell it was Bob who signed it, but can tell that someone in the ring signed it in there. So we get anonymity, unforgivability, and collusion resistance from them. So in this way we can hide the transaction sender by grouping together people with a similar amounts of spend as me, so that when you see the transaction you can't tell it was me that actually was the one who created the transaction. Okay, so it basically just creates a ring. We take the public keys of all the entities apart from ourselves, and we add in some sort of public key. It's about 5 or 6 lines of Python code, so it's not too difficult to do it. But that creates this ring signature, and then that's added. And then the other thing that we use is what's called a stealth address. If I want to hide the recipient, then there is some negotiation between the sender and who's going to receive it, that we will generate a new cryptocurrency address. Victor, in this case, knows where that address is. Bob sends the money to that address. Victor then takes the money, and because again he's a ring signature, then he hides his ID. So in this case, the stealth address is used to be able to hide the sender or the recipient, the recipient of the transaction. The ring signature is used to protect Bob, because we can't tell. We can do other little smart things like putting a little special label onto a transaction, and then only certain people, if they're watching, can actually see that little label occur. Okay, so you're interested, that's all done through the Curve-Diffie-Hellman. Bob can't tell the address that Alice is going to receive the bitcoins on, or the cryptocurrency. So when he sends, he will send to an address, and Alice will pick it up. Obviously, Alice needs to remember where that address is, so that when the transaction happens, she'll be able to take that cryptocurrency. And that's it. Does anyone have any questions on that? Nope. Is my microphone still working? Can you just say hello?
Yeah, it is working.
Thank you.
Yes.
Okay. Well, I go into Coursework now. Is that okay? I'll give you a heads up on that. Okay, so we've got some people connected, which is great. So you'll find, I mean, the great thing about this is that with whoever is that account, if you could maybe type, can you type into this? You should be able to see in real time someone updating the code. Ah, good. So we've got we've got a little example there. I'll change that back to Fred Smith. So you can actually see the history of documents.
That's my paper. You can't change that.
I know. I'm sorry. I'll change it back again. The history is quite good. I can go back and I can reset it back again. Yeah, it's quite good for version control from in there. So it's up to yourself if you want to use LaTeX. It's useful when you get to your dissertation, when you're writing courseworks, and obviously in your work if you're writing reports that have some literature review in there. It's your call. There's a little bit of learning, but I can assure you once you get over that little bit of learning, it's a fantastic, amazing thing. So I back up to a GitHub. So when I back up, I create a GitHub, and then it will then synchronize to the back end GitHub, and then I keep pushing updates. So when I'm happy with a version, I push a version to GitHub. If the GitHub gets changed, then I've got to pull it back. So if you're working with other people, they might update the GitHub, and in your case, you would pull it. So that means that if you make a mistake, you can backtrack to a previous version quite easily. Does someone have a question? So I've laid this one out single column. You might like the double column version of it. That's like the IEEE journal. This might muck up a little bit because I had to change it a little bit. Yeah, so I think I need to bring the title back in for that one. So the double column looks amazing, but it can be a bit difficult to do your diagrams, but I can show you how to do diagrams that go across the two columns, but maybe you just want to use the single column version just now, but it's so easy to be able to move back and forward and create different format, use different references. So in this case, I'm using IEEE. You can use APA if you want, and it'll all automatically code them for you, put them in the right format. So the way that you do your main section, so you recompile each time, and it should show you the errors that you've got in there, and that's fine. Okay, so you'll have your abstracts there, and then you just create your section and then a subsection and so on, and it should all do it for you. If you don't like the text version, then so it should automatically number it for you, hopefully. There we go. And format it for whatever style that you want. You can put in a table of contents, and you can have footers and things like that. So where it's most powerful is when you get to your bib. So the bib is where you find your the format for your papers. So the way I usually do it is Google Scholar. From here, try to always use Google Scholar, but just kind of use Google, and I'll go for lightweight crypto, and we'll go for low power. Say, I look at this number here. 395 is a pretty significant paper. It's published in 2017. Might be a little bit old. Well, it is if it's a survey, so it's probably a bit out of date. But there might be something interesting in there. So let's find. We could maybe go for 2015, and this looks like a fairly good paper. Typically, you start off with a review paper, and maybe just refer to that. Most papers will be self-archived, but if they're not, you can go into the Napier system and get it through IEEE or ACM. So if I take this one here, then what I usually do is I grab, you can either grab the APA format if you use an APA and paste that in if you want. The way I do it is to grab the bib. I take that, I put it into overlay. Yeah, and you see that's called Rani. So I'll go here, and then we just say site, Rani, and it comes in like that. And it should automatically number it and put it into the end of the paper. So where did we put that one? Here, there's number 1. And there it's there. And then if we want, we can change the APA or anything like that. If you've got a web link, you add that as miscellaneous. And you just add your link in here with a title, and it will come in automatically. You can make it clickable if you want. You can make it different colors, and it should come in that one there.
Sorry, Bill, how do you
Yeah.
access IEEE through Napier then?
Okay, so just let me show you that. So IEEE Napier library. Hopefully we'll be able to find it here. So that one, and then you should go through your authorization, single authorization, and that's in. So you don't have to log in to the main site. It's all done. So if we look for crypt lightweight, cryptography. See, you've got the logo, the university access there. So it's just a little bit slow. It goes a bit slow at this time. Okay, so we like that paper, and then we click on it, and hopefully, hopefully it's going to appear in a little minute. It should. Just let me see if it's downloaded it here. There it's there. And you should get the full paper. I appreciate some of the papers are quite kind of heavy on the maths. Try to read around that and to see if you can just understand what the paper is actually doing. I've not picked a good example here, but you probably want to be just picking off from the abstract what the key things are about the paper and why they're important to lightweight cryptography in this case. Does that show? And you can do the same for ACM and the other ones. And most papers are on ACM and IEEE. The Elsevier ones can be a bit sticky, but Google Scholar and ResearchGate are 2 places that you would typically go to find papers that have been self-archived. So in here you might be looking for, can we find a subject? Let's find mine then. There we go. So you should, most researchers will self-archive their papers, and if you can't get the paper, then you just contact the author directly and then just tell them that you're working on a coursework, and usually they'll help you from there. Okay, does that help? Oh yeah, here we are. So you can get ACM, Science Direct, which is the Elsevier ones, and Springer. Springer have got some really good journals and ebooks. Okay, so section, and it's a matter of just Googling. You can make fantastic looking code. This is what publishers use when they're laying out books and so on. So you can virtually do anything in there, but you can easily break it. So you might want to have backup of your code. You can download the zip file from the menu. You download the source code, and you can keep yourself a zip file if you've got another LaTeX system there, or just to keep a backup. But obviously you can use GitHub to push your code, create your repository, and you can push your code back. If you use something like this, you can make it look all colorful, so that this import knows the keywords and can make them colored, so you can make it red and for import and so on. When you're doing a table, either just take a screenshot of the table and put it as an image, or the proper way to do it in LaTeX is with the ampersands like this, and that gives a number of columns there. You then put a caption on the table, and then you use ref, and your table should come up, and it'll automatically number it. Because you're probably not going to have a lot of figures, you could just do that manually, but if you have a big dissertation, it makes it a lot easier. You can also compile your list of tables in there too. For the graphics, normally we create a folder, and then we just upload our graphics into there, either from a URL or from a local computer. Once they're in, we just define it here for that link, define the width. If we use the star will generally use the full page, and if we don't, then it will integrate in with the text. We add our caption here, and we get a reference, and then we just refer to it here. So I think it's a good way to write. If you don't like the text-based, then there's a simple editor that you can use, a graphical editor. It's not great, but it's something, and you can do that. I use it for bullet points mainly. So if you look, that's what the bullet points look like. So rather than me just typing in these things, I might just add them and like that, and you should see that reflected into your PDF. So that's one way of doing it, and if you want, then you can create your own and then share that with me, and then I could review it if you wanted. It's a maximum of 15 pages, but it's not. Even if it was 12 pages or 10, if it's quality, then that's all that really matters, and you shouldn't try to just fill space. You can take double column if you want to, if you've got even more than 15 pages. But maybe the sections that you want is a basic abstract, just defining the problem, what the focus is of your coursework, what you're going to show, what you're going to implement, and what your main findings is. Then a basic introduction to just lay out what the thing is you're working on. In this case, it's lightweight crypto, give an introduction to it. You'll then go into literature review or related work. Some people call this the state of the art or background material, but it will generally just go into look at the papers that are published and to give an overview of some of the research work that's actually going on. Then in the third section, you'll grab your GitHub code, and the code might be massive, but you might just take a little snippet of the code to say that this is how the keys are created, or this is the little magic little bit that makes it all work, and this is how it works. But you would make sure that you give the reference to the GitHub that you took it from, and you've got to define authorship. So if the authorship is not defined, we assume that the code is yours and you've generated it, but then obviously if we find out that that code has come from somewhere else, then there's a lot less merit to that. Then in the next section, you've got testing, and testing maybe grabs some test vectors for lightweight crypto, like for the word hello, for a lightweight crypto method, and then just proves that you get the right output. So that's a validation test. The next part is an evaluation where you might run the test 1,000 times and see how long it takes to run, find out minimum and the maximum time and the standard deviation and the average. Or it might be running a crypto method in a browser and running it until the battery on your phone goes to 10% and measuring the time, and then keep repeating that experiment maybe 10 times and then see how it works. So your benchmark would be to run it without crypto, run the battery down, and then to run it with crypto and see how long it takes. And then you can see that the difference is 50% in energy consumption for an Apple phone with a certain ARM architecture. If I use Chrome, but then if I use Firefox, it lasts 25% longer. And in the end, you've got your conclusions, and then you've got your references after that. So the submission will be with a PDF, so you'll submit it as a PDF output, but it would be great if you can actually put in a reference to your own GitHub so that I can go and have a look and see your code if I need to, and just to see that you've planned it well and you've got running code that works. If the code doesn't work, that's fine, and it can be quite challenging, especially if you pick something like homomorphic encryption to actually get it to work. So even if it doesn't work, you say I tried and here's the result I got, and I think the problem is this, and it's just not working. But here's a simpler example in the evaluation. It's not what I wanted to do, but this is my alternative to it to show that I have evaluation skills. Any questions? Is my microphone working? Somebody say hello.
Yes,
Yeah, but
it's
I-
working.
Yeah, sure.
Good. Okay. Maybe everybody's gone, and I'm just talking to myself here. It won't be the first time, so good. Okay. So we've got a wee while to do this, but really I advise you to pick your subject and find some GitHub code and get it downloaded. And if you have a problem, just give me a shout, and I can share. If you add me onto your GitHub, just find my ID. You can share three accounts on your GitHub, and it'd be really interesting if you can sync your LaTeX into a GitHub and then add your code there, so that I can just go there and I can create an overlay from that, or you can share your overlay if it's really up to you what you want to do. The marking schedule is there, and it's 20% for your JIT. It's not marked within sections, it's more of the feel of the report, the quality of your research that you've undertaken. Do you refer to research papers and rather than just Wikipedia? So I know that Wikipedia is the font of all knowledge, but actually it's not great. Sometimes it's best place is really the original source of the information. So if you can refer to academic papers, you can have some links in there, but don't link to cisco.com, and don't give us a link to a big massive page that is difficult to see what it is you're pointing to. If you can use academic work, then that's peer-reviewed academic work, then that's great. But obviously, probably about half of your links are just going to be GitHub links and so on, or white papers. So then there's a clarity of the implementation, and that's your little explanation, how good you are at explaining some quite difficult code, difficult concepts. Give the reader a pointer to the main guts of what's going on in the code. Level of innovation, have you thought of a new way of evaluating? Is it interesting? Isn't just not that you're running it on your laptop, but you've actually went that extra few inches to try it on a Raspberry Pi or on different computers or something, or the cloud. It's really up to you if you want to spend that little bit of time and effort on that. There's the quality of the evaluation, how good are your tests, and the evaluation that you've conducted. What's your conclusions looking like? Have you found something new? And then finally, we'll give you 15% for your presentation and the usage of references. And then, so that's to be handed in the Monday after week 15. I've got a number of topics there. You don't have to stick with those ones. You can create your own one, but you've got to get it approved by me that there's enough merit in it, and it is related to cryptography. Anybody, any questions? Good. So you can also do this in Word, so there's no problem in doing it in Word, and you can use a referencing system in Word. I find it horrible. I find doing equations in Word a nightmare. You'll find that LaTeX is much better, more standard in terms of doing little equations. If you have to, you just do the dollar y is equal to x squared plus c underscore 1, and then that should come through as a little equation. And so it's just so much easier than having to use that horrible GUI in Microsoft Word. If you want to change your style, you can add different formats here, and it's really easy to change that. Any questions? No? Good. Does anybody have any questions about anything on the course? Anything? Anything that you're unsure of? I appreciate you're probably having a little rest after the test, so but you have to sort of schedule yourself back in to get back in sync with the labs and certainly with the coursework. Test you could probably leave for a little while, but certainly look at the coursework and ask questions now. Okay, good. Right. Well, thanks very much for joining tonight. And if no one has any more questions, you are still there, yeah? Say hello.
Yeah.
Good. Excellent. Okay then. Right. Well, I'll see you next week. I think next Tuesday's okay for me. So we'll be back on the Tuesday again. I was in Plymouth yesterday, so that's why I couldn't make that one. So I was traveling. Normal next. Okay. Remember, we have the Slack channel if you need to ask any questions at any time, and if you've got anything to share, then please go on to Slack and do that. Okay.
Thanks, Bill.
Thanks very much. Sorry for taking so much of your time tonight. I know you're all very busy people, and I appreciate it. And thanks for all your hard work and effort and great questions on Slack. Okay. Thank you.
Thanks, Bill.
Okay. See you next week.
Bye-bye.
Thanks.
Cheers. Bye.